All right, here we are again. We got particle energy and momentum homework set for dynamics. Uh, Here in the first problem, we have a stationary bridge that is having a bucket that is extended down 30 feet. We're given some certain values for these for the bucket as it is moving, and we're asked to find the max horizontal distance through which the bucket will swing if it ever comes to a stop. So basically we can set it into two different free body diagrams. One as it is in the stationary position as it is moving forward, but then also as it stops and it swings forward. And so we want to know the distance, this distance d, and so we set up a free body diagram basically as a right triangle so we can figure out that d, that distance. And so using the few different equations from the book regarding kinetic energy of a particle and work and energy, we're using this u from point 1 to 2 is equal to t2 minus t1. And we can manipulate these equations for what we need to find. So u from 1 to 2 is also equal to negative mgh, which we're able to calculate very quickly. And plugging that in to the T1 in this case, and from the book, is equal to 1/2 mv squared minus the mgh, which we found. Then manipulating that to find the height, this distance h that it moves up as the bucket swings, we're able to find the height at 1.5528 feet. I just kept it a few extra points for extra numbers just for calculation purposes. Then from there we can plug it into the Pythagorean theorem, and thus we are able to find that our maximum distance is 9.53 feet. Moving on, this next one, we're given a truck that is going up a 2% incline. We are given that the velocity at before it gets onto the incline is 72 kilometers per hour, and as it is going up, the second velocity is 108 kilometers per hour. We're given the masses and we know the distance, so we're using these same equations as before, as t equals 1/2 mv squared, and t2 is equal to t1 plus u from position 1 to position 2. We're asked to find the average force of the wheels at the wheels of the cab and the average force in the coupling between the cab and the trailer. So here we can break down our different values that we are given into some more easy to work with numbers here. And then from that, we're able to plug them into what we want to find out. So again, manipulating the T2 equals T1 plus U from position 1 to position 2, we are able to set it up in such a way that we can find the force at the wheels. That's denoted by F sub T. Again, then manipulating this equation, we can set up to find F sub T and then plug in the values. So as we have 1/300 meters times 1/2 times 7,200 kilometers times 30 meters per second squared minus 1/2, so on and so forth. And we were able to find that the average force is equal to 7.41 kilonewtons. Then moving on, we're able to see that for the average force in the coupling between the cab and trailer, again using the information that we know, and this weight is calculated by multiplying this 5,400 kilograms by 9.81 meters per second squared. Again, doing the similar thing as we did in part A, setting up the equation and then solving for the force at the couplings. And plugging in our values as you see here, and we are able to find that the force at the coupling between the cab and trailer is equal to 5.56 kilonewtons, and that is in tension. Moving on to our third problem here. So we have 3 trains, which each weigh a different amount of tonnage. And they're all moving at 30 miles per hour. As we set our coordinate system, as positive is to the left, and we are given a kinetic friction coefficient of 0.35. And just as we use the U from position 1 to position 2, we can use it in a velocity setting, which is equal to the force at A times distance, or which is equal to negative mu sub k times the normal force at A times the distance. Here we're being asked to find the distance required to bring the train to a stop and the force in each coupling. So using a free body diagram, we're able to find the values that we're able to work with in a bit easier fashion here, rather than just using 40 tons and 50 tons. Break that down into kips. And from there, we're able to use we're finding the force at A that is acting on on that car as mu sub k times the normal force at A is equal to 28 kips. And from there, we're able to break down this 30 mile an hour into feet per second. So I'm plugging all of that in using the similar equation that we used in the previous 2 problems. We're able to manipulate the equation such that we can find D, and plugging in the values, we find that D is equal to 279 feet, which is in order to get the train to stop. Next, finding the force in each coupling. It's a little bit trickier, as there is just a coupling there between A and B and C. Excuse me. Again, using the same equation as we did in part A, plugging in our values and manipulating the equation in the way that we need to, we're able to find that the force at coupling AB is equal to 19.38 kips, which is acting to the left, or in compression. And then at car C, or couple BC, once again, plug in the values and manipulate the equation to find force at BC is equal to negative 8.62 kips, or force at BC is equal to 8.62 kips in compression. Moving on, it is someone drops a ball, and it goes in a counterclockwise motion. And we're given the velocity, the downward, and the length from point A to the origin. From here we can somewhat tell the equations that we'll use, as they are similar to the first three problems that we've looked at already. And so we're being asked to determine the angle theta at which the rope will break, knowing that it can withstand a max tension equal to twice the weight of the sphere that is being dropped. So if we draw a simple free body diagram, here we plug in the values that we know. Position 1, there at A, 2 meters away from the origin, and then position 2, there at some distance theta away, which I did not add theta in there, so I will go ahead and add that real quick. So they're at that distance theta. Then again, plugging in what we know, we find that T1 is equal to 12.5 times m. And also moving to the U sub 1 to position 1 to 2 equal to mass times gravity times delta y, or in our case, it is length times sine y, Earth times sine theta, which is then equal to 2 mg sine theta. Using this same equation, T2 equals T1 plus U sub 1 to 2. Plugging in our values, we're able to find a v squared equation as 25. V squared equals 25 plus 4g sine theta. And that's our first equation. So looking then here, treating it as a point, is basically a point particle, and setting that to the normal tangential coordinate system. We're able to use that and plug that in to a similar equation as we did above. And again, putting in the values that we know and manipulating it in such a way to find a second velocity squared function, we find that our second one is v squared is equal to 4g minus 2g sine theta. Setting our two v squared equations equal to each other, we're able to then plug in the values and manipulate it so that we can find the theta is equal to the inverse sine of 4g minus 25 over 6 times g, which results in our theta being 14 degrees. Here in this next problem, we have a ski lift that transports 1,000 skiers per hour. We are given the distances that we need and some additional information in regards to the average velocity and the mass of each skier. We're asked to find the average power required and the required capacity of the motor if the mechanical efficiency is 85%, and what would happen and if a 300% overload is to be allowed. So here in this first part, we use our average power equation as delta U over delta T. So as we know that there is 1,000 skiers per hour. So that 1,000 skiers per hour needs to be multiplied by the mass of each skier times gravity times the height of the lift. And thus we have, when we plug in the values, as we convert hours to seconds, thus we find that average power is equal to 57.2 kilowatts. Here in part B, with a 300% overload and the 85% mechanical efficiency. So a 300% overload needs to be added to the 100% load that is already being applied to the ski lift. And then multiplied by the average power, which gives us the power at 300% overload. And then to find the required capacity at 85% efficiency, we take that overload and divide that by the 85%, thus giving the capacity to be 269 kilowatts. And this next question got a little bit trickier, as we are given this collar attached to a spring and a pin and going around a certain a bar, kind of like one of those kids' toys. We're given the mass of the collar at 2 kilograms and the spring constant at 600 newtons per meter. Again, looking at the using the book to find some as well as notes to get some of these equations, such as the V sub E is equal to 1/2 K times delta X, and V sub G is equal to mg Y. And here in this question, we're asked to find the velocity as the collar passes through B and as it reaches C. So here what we can do is we can break it down into a few different parts, such as the elongation from the origin to point A, and then from point C to from point B to point C. There we can use the values moving forward through the rest of our calculations. Here we find the potential energy of the springs using the 1/2 K delta X equation. So the potential energy of the spring at position A is equal to 3 joules, and at position B is equal to 0.75 joules. Then going to the potential energy of gravity, we're able to find that gravity at point A and C is equal to 0, and at point B is equal to negative 3.924 joules. And using this, we're able to use kind of a different equation that includes gravity, as gravity is acting on this collar, and so it is creating some type of work on it. And so we have T sub A plus V sub A plus the velocity V sub G at A equal to T sub B plus V sub B plus V sub G at B. plugging in our values that we have calculated out already, we find that the velocity as it passes through B is equal to 2.48 meters per second, and that is obviously acting to the left as per the diagram that we were given. Using the same equation and plugging in our values to find the velocity as it reaches C, we find that the velocity as it reaches C is equal to 1.732 meters per second in the vertical direction. Continuing with another spring question, we have a box sliding down an inclined plane at 20 degrees, and at this point is 8 meters away from the spring. The initial compression is 50 millimeters. The box has a mass of 50 kilograms, and the velocity is 2 meters per second. We have a spring constant of 30 kilonewtons per meter. And again, using similar equations as we did in the last question, we're asked to find the maximum additional deformation of the spring in bringing the package to rest. So we can find a lot of information by drawing a simple free body diagram. As we have two different heights, one where the box is initially at the start of at 8 meters away from the spring, and the second as it comes in contact with it. And so we need to find this distance x. So first, finding a few simple things such as the height at position 1 and the height at position 2, and of course the weight of the box itself. Using this information, we can move into the T1 plus V1 equals T2 plus V2 equation. Which is the conservation of energy. And again, adding in the gravity constant, as gravity is also acting on it and doing some of the work. We're able to plug in our values that we know, and we are able to get so after all of this algebra going through, we're able to get a quadratic equation. And then plugging that into the quadratic formula, we're able to get that x is either equal to 0.2688 meters or x is equal to negative 0.3576 meters. Obviously it cannot be negative, and so our distance x, or the max additional deformation, is equal to 0.269 meters. And now moving on, this is where we get into the momentum portion of this homework set, as we have another truck going up a 15-degree incline. So we're given the mass of the truck at 10 tons, initial velocity, and time before the velocity is reduced to 36 feet per second. Sorry, I had to read my handwriting. It was a little jumbled together there. So using this equation that we are given from the book, mv1 plus IMP, which I believe is the impending momentum, from position 1 to 2, is equal to mv2. So it's very similar to the equation that we used several times, is the U from position 1 to 2 and T1 and T2. So we're asked to find the magnitude of the braking force and the additional time required for the truck to stop. Using a superposition and breaking it up into 3 separate free body diagrams, we're able to see things a little bit clearer. So there we have all of the forces that are acting on the cab of the truck, actually on the trailer. We find that the weight of the trailer is equal to 20,000 pounds. We have the weight, so the mass is equal to the weight divided by gravity. And the impulse direction in the x direction, we plug that in using what we know from our free body diagrams, and we manipulate the equation in order to find the force, the magnitude of the braking force, which is what we were trying to find. So as we plug in this and then substitute in our values here and here, we're able to find that the force is equal to 2,280 pounds. Now to find the additional time required, we set MV1 to 0, and we manipulate this first portion of the equation that we just used so much that we can find the time required, or our final time. So our time is equal to mv naught over the force that we found plus mg sine of 15 degrees. Plugging that in, we find that t is equal to 9 seconds. And so using that our initial time is 6 seconds, we find that the additional time required is 3 seconds. Well, this video is going on a half hour, so I'll try and move a little bit quicker. So we have a pulley system that is similar to the free weights or the cable system that we looked at a couple homeworks ago. Of course, we're given the different weights of the collar and the weight that is suspended. This time we're being asked to find the time at which the velocity of the collar B will be at 2.5 meters per second to the left. And from there we are asked to find the corresponding tension in the cable. Setting up a free body diagram of the whole system. Here we see that there's two tensions going in the same direction. And breaking this down even further, for collar B, we can set it up in a superposition type problem. And from there, we see that we can find a first equation. So 150 T minus 2 times tension times time is equal to 20. Then using a superposition equation for the weight at A, we're able to put that into a similar type of equation, finding that the tension times time minus 29.43 times time is equal to 15. And so setting equation 2, plugging in 2.5 meters per second in order to find the time at which the velocity of collar B is equal to 2.5 meters per second. We take the second equation, multiply that by 2, and add equation 1 to it. And thus we're able to get the time that color B is equal to 2.5 meters per second is 0.549 seconds, which is relatively quick. And then from there we're able to find the tension in the cable as we use equation 2 and plugging it and manipulating the equation to find tension. So plugging in the values that we find for time, we're able to find that the tension is equal to 56.8 newtons. Moving on, we have a bullet going into a ballistic cube. We're given some certain values as far as like the mass of the bullet and the block and the length of string and the max theta. So here we're using similar equations that we've used throughout this homework and throughout homeworks in the past. So we're asked to find three things. First, to determine the initial speed of the bullet, V0, the impulse imparted by the bullet on the block, and finally the force on the cord immediately after impact. So we can set up once again, another superposition free body diagram in order to get a first equation as m sub a times V0 is equal to V1 times m sub a plus m sub b, as m sub a is equal to the bullets and m sub b is the block. So in using this, we can find our V1 and plugging this into the similar equation that we have used in past problems. We can find that V1 is equal to the square root of 2GL times 1 minus cosine theta. Now that we have V1, we can plug that in and find to this first equation and find V0. Once again, manipulating it and then plugging in our known values of what we have, we're able to get that V0 is equal to 778.92 meters per second. This is possible if we use the full calculated value instead of the rounded value of V1. For part B, finding the impulse imparted by the bullet, we use this portion, the integral of the force of F dt is equal to m sub b times V1. So it ends up being 4.646 joules, as the mass of the block is equal to 1 kilogram. The force in the cord, we set the coordinate system to the normal tangential once again. So we have T, the tension, minus gravity times m sub a plus m sub b equal to m sub a plus m sub b multiplied by v squared over the length. Manipulating and plugging in the known values, we find that the tension, or force in the cord, is equal to 19.74 newtons. Here on our second to last question, thankfully. This one was quite difficult, and it took me quite a while to understand and do. So we have one of those clacker ball things. And so we have a few given values and instructions. So we're first asked to find the velocities of A and B immediately after the first collision, and then the velocities of B and C after the second collision. Then we have parts C and D, which have been recommended that we try for fun. However, I did not have the time to do that, but I will most likely be taking a look at that and trying to do it if in studying for the upcoming exam. So here is the parts C and D. So first, to solve for parts A and B, really, we set up a free body diagram as before the collision is equal to the immediate collision. So we have the mass times velocity at A and mass times velocity at B equal to mass at A times V prime plus mass at B times V prime at B. So these primes are denoting the velocities of A and B immediately after the collision. So we can simply put them at V naught is equal to V prime of A plus V prime of B. And we can manipulate that to solve for another equation if needed. Now this relative coefficient was really interesting, and I'm not still entirely sure how it works because the book was not too clear on that as to why it's being used. Mainly it was just kind of plugging that in and it reverses the signs of what V naught is equal to. I'm not really entirely sure why. And so from there, we're able to plug in a manipulated version of our first equation into the second relative equation in order to find V prime of A, which is equal to V naught times 1 minus E, or the coefficient of restitution, divided by 2. And then plugging that into the first equation, the manipulated equation, we're able to find that VB prime is equal to V naught times 1 plus E over 2. And continuing on for part B, as we're looking for the velocities of B and C after the second collision, we really follow a similar process, but this time instead of VB prime, we have VB double prime, as it is transferring the collision into sphere C. There we get our third equation, and again using the relative equation, we're able to get our fourth equation. Manipulating that, we can find V double prime B. So in plugging this V double prime B in, we're able to find our V C prime. So plugging that in and doing a little bit of algebra, we're able to find that VC prime is equal to V naught times 1 plus E squared over 4. And from there we can plug that in to our equation above, and we find that V double prime B is equal to V naught times 1 minus E squared over 4. Now in this problem on the assignment, it said that there was a mistake in the solution manual. I've checked that, and I've also checked Chegg and a few other places to see if there was any inconsistencies, but I wasn't able to find any. So if I did any part wrong, I have no idea. Oh, goodness, now we're at 40 minutes. All right, thankfully, last question. So we have a ball or a sphere attached to a string that is not in contact quite yet with a block. And as the block gets pushed at 2 meters per second, it extends the ball up a certain height and moves the block a certain distance. We're given a coefficient or a value for the E, which again I'm not sure what that's called, and for the kinetic friction. So using similar equations that we've used in the past throughout this homework and in past homeworks, we're asked to find the max height h reached by the sphere and the distance x traveled by the block. So with the free body diagram after impact, and using a similar equation that we used in the previous problem to find the max height, we once again set it up the same way. And we're able to find the first equation, v prime a plus 2 vb prime is equal to 4. Using this relative equation once again, we get our second equation as v prime b minus v prime a is equal to negative 1.6. And manipulating that for vb prime, we plug that into our first equation, and we find that v prime a is equal to 2.4 meters per second. And plugging that into our v prime b, we find that it is 0.8 meters per second. Using both of those values, we plug that then into the conservation of energy equation. And we find that V2, so we have V2 is equal to mass at A is multiplied, the velocity V sub 2 is equal to mass at A times gravity times the height. So we're looking for the height, and so I'm putting in our known values and solving for h, we find that our max height is equal to 0.294 meters. Continuing on to part B, we transfer over the information that we've gained from part A, and now we set up another free body diagram for the distance of the block. Setting left to the left as positive, as our positive direction, we can find everything that we really need from this free body diagram. Again, using the energy and work equations that we have used in the first part of this assignment, and setting T2 equal to 0, we have 1/2 mb times v prime b squared minus mu sub k times mb times g times the distance x that we are searching for. There we manipulate the equation to solve for x, canceling out and doing simple algebra. We're able to find that x is equal to 0.0544 meters, or 54.4 millimeters. I know this was kind of long, but it was a very long and difficult assignment to do, especially because it was so different from physics 1, momentum and energy. But I hope this helps. and I hope you don't mind 45 minutes. Thanks.